Hi guys, this is Pranay. Currently, I'm in the second year pursuing BTech in computer science. Today, I'll be teaching you guys a very simple topic of algorithm, that is asymptomatic notations. It is very crucial to learn about this topic cause it helps you in solving time complexity problems. So, let's get rolling. Hi friends, today I'll be talking about asymptomatic notation. It is a very basic topic and an important one to understand time complexity. We have to understand asymptomatic notations first to solve questions on time complexity. So these are my handmade notes on asymptomatic notations. I'll just walk you through my notes. So these are my notes. Now I'll give you some insights on my notes and will tell you more about these notations. So what does a asymptomatic notation mean? It basically means it just gives you an idea about how good a given algorithm is compared to some other algorithm. Basically, in a very simple language, it just tells us about how a algorithm differs from any other algorithm. There are three types of asymptomatic notation. The first one is big O notation, the second one is big omega notation, and the third one is big theta notation. Big O notation is the widely used one. Now I'll talk about the big O notation. Big O notation is used to describe asymptomatic upper bound. Basically, in class 12, you must have studied about upper bound, lower bounds, maxima, minima. So it talks about I'll in the next section I'll walk you through the graphs of all these three notations. It will help you understand better. So first I'll just tell you the definition of big O and then I'll walk you through the graphs. So big O notation is used to describe asymptomatic upper bound. Mathematically, if consider a function fn describes running time of an algorithm. Basically, consider a function fn which describes the running time of an algorithm. So fn is big O of g of n. G of n is another function. G of n here is another function. So if there exists positive constants c and n naught such that fn lies between the gn, g of n and 0 for all n greater than equal to n naught. Here n used to give upper bound on a function. Here n, so it just gives us the upper bound for a function. Basically, if we see here, g of n is another function, or big O of order of g of n is giving you the basically the time complexity of the function. So f of n is the running time of an algorithm, and we are supposing in here that order of g of n is the time complexity of this algorithm. So now, if we see if fn lies between 0 and the g of n function for all n greater than equal to n naught, then the function is big O of n or the function is big O of n square. Basically, now I'll tell you about the graph of big O. Now, in this case, you will understand it much better than the definition. Suppose we have a function f of n, the one I am highlighting with my cursor. It's f of n. And we have a point here n naught. It's a graph between time and n. I already told you about n. So the function constant with g of n after a certain point n naught, if this function the g of n always stays above f of n, that is it is the upper bound of f of n, that speaks for the answer. So after this point n naught, if the function stays above f of n, then it's a example of big O. Basically, it only gives us the upper bound of a function. Now, the second notation is big omega notation. Just like big O notation, it's just like big O notation. As big O notation provides us with the upper bound. On the other hand, big omega notation provides us with the lower bound. So, if you see the definition, it's similar to uh, big O. It's very similar to big O, but the case which differs in this case is it tells us about the lower bound. So I'll not explain you the definition because it's very complex and you will not understand it very clearly. So I'll just walk you through the graph of big omega. So similarly, here is the graph of big omega. It's the graph is of time and n. Now consider a function f of n, which is the running time of an algorithm. We already know that. So f of n. Now there's another function g of n with a constant c. Now if this function f of n, now this function f of n, wait, yeah, right. So now let us consider a point n naught. From this point n naught, the function g of n will not go above the function f of n. That means that means g of n is the lower bound of f of n, which speaks about big omega, which tells us about big omega. So after this point n naught, the graph of g of n, the line of g of n, will always remain below the function f of n. That's it for the big omega case. And now I'll talk about the big theta notation. Uh, Sorry, I forgot to mention big O. Yeah, yeah, big O. It's most widely used notation because it tells us about the worst case of an algorithm. And if we solve the time complexity of an algorithm, we always solve for the worst case. So big O notation tells us about the worst case. Big omega notation tells us about the best case. And big theta, I'll come to it after I explain you the big theta notation. So basically, big theta. Let's take an example. Big theta, it's the average case of both the notations. Basically, the thing is, big theta lies between both big omega and big O. So basically, let me walk you through the definition. Let us define f of n, run time of an algorithm. F of n is said to be big theta of g of n, if f of n is big O of g of n and f of n is omega of g of n. Like I told you, it just it's just the average case of both the notations. So this is how we can represent it mathematically. Now this is all about mathematical notations. Basically, it simply means there exists a positive constant c1 and c2 such that the function f of n is sandwiched between c2 g of n and c1 g of n. Basically, c2 c1 are the constant. constant. Now, this is the this is the best thing you will get in here in my notes that so I explain everything with graphs because mathematical expressions are very complex and they are not easy to understand. So let us see this graph. So yeah, let us see the graphical example of bit theta. Suppose there is a function f of n. Okay. There's a point like always and not. So the function f of n is sandwiched between the two given functions like c1 g of n and c2 g of n. In the case of big O, the function g of n lied above the function f of n cause it was the upper bound. And similarly, in big omega, the function g of n lied beneath the function f of n cause it used to give the lower bound. But in the case of big theta, the function is sandwiched between both g of n, both both the function g of n. The only thing that differs here is the function is same, but the constants are different. The constants here are different. Now, which one of these to use? That's a very nice question. Now, the question which one of these to use, I've already told you about it. Since big theta gives us a better picture of runtime for a given algorithm, most of the interviewers expect you to provide an answer in terms of big theta when they say order of growth or order of what. Basically, all these terms, big theta, big omega, big O, they are pronounced as order of. So as big theta is the optimum case, most of the interviewers will ask you about the big theta, order of in terms of big theta. But but in practicality, we don't calculate big theta. The only focus of an algorithm and the time complexity of an algorithm is to calculate the big O, the order of big O, because big O gives us the worst case, and that's very practical for an algorithm to find the worst case. So we always find the worst case. Just remember this. So yeah, a quick question for you guys. Prove that n square plus n plus 1 is order of n cube, omega of n square and theta of n square using respective definition. This is a quick quiz for you guys to solve. Now, this is a very important part. This gives you the increasing order of common runtimes. If we go left to right, then we are going from better to worse. So the constant runtime of an algorithm is the best. Then comes the log n thing, then comes the n log n square, n cube, 2 is power n. The worst case is exponential. That is here. This is the worst case. That's it from my side. I hope you understood the concept of asymptomatic notations. It's a very easy topic, but it's a must for solving time complexity. I hope you liked my video. Thank you so much.